Welcome to FLIR Teledyne's webinar on integrating AI into camera systems. My name is Arthur Stout, and I'm the Director of Product Management for Teledyne FLIR's Artificial Intelligence Solutions in our Santa Barbara, California facility. As I meet and speak with customers, I continue to learn how similar our AI requirements and development experiences have been. Over the past 6 years, Teledyne has made significant investments in AI technology and built a team of world-class experts. Today, we are a recognized leader in imaging AI. I'd like to start the presentation with some examples of applications we're working on to bring the power of deep learning to our customers. We focus on defense, autonomy, drone detection, security, and smart city use cases. And as you can see, we've created AI software for both visible and thermal cameras. This first video demonstrates our friend or foe detection algorithm, and we show the target class, the confidence score, and a fine grain classification, which in this example is a gun, further classified as a rifle. The second video demonstrates our military vehicle and intrusion detection algorithms. We also have extensive experience in ADAS and automatic emergency braking applications. Here you can see we have identified the vehicle. We're showing the confidence score, and we're tracking small observers or people. And again, you can see we're able to pick up targets and do classification at very long range, very small pixel count. This statement by Geoffrey Hinton of Google helps us give some context in the relationship between processing power, data, and algorithm capability. Of course, edge product design is extremely constrained by computer power and is what Teledyne FLIR is focused on. With the development of neural networks over the past 10 years, there's been an accompanying effort in hardware development. Today, GPUs dominate the processor market for intelligent camera systems. However, they are very expensive and consume a lot of power. The ISP processor industry is responding to the demand for low cost and low power and are bringing new silicon to meet the industry's needs. CPUs are very low compute density, and they're really designed for serial processing. GPUs have very high compute density and are ideal for parallel processing, of which neural networks, that's how they run. To give some context for the performance of a GPU power over a CPU, we ran a popular neural network called ResNet50 on a PC and on a GPU, and the routine ran 72 times faster on the GPU. And the hardware that we ran, I referenced down below, if anyone's interested. Here's a graphical representation of a neural network. At each layer, a series of convolutional computations are performed. For detection, a video frame is fed into the network. The first step in the process is to segment the image into sections. Neural networks come in a variety of input resolution, as small as 16 by 16 to over 512 by 512 pixels. The pixels in each segment are inputs into the convolutional calculation, and the output of this calculation is feature extraction. Things like lines and shapes, for example. As the data moves through the network, associations between the features is accumulated with the final output, a classification of the object. The input resolution and number of layers in the network determine the computational demands to run the network. Therefore, developers must balance the performance expectations with the processing power their budget can afford. This table shows the computational demands of networks that Teledyne FLIR is deploying in systems today. As you can see, our proprietary FLIR robust network runs at over 13 gigaflops per second. To help put that into context, our sophisticated local area contrast enhancement algorithm, standard on our camera cores, takes about 1 second to execute. A small efficient network like ResNet 50 takes over 16 seconds to execute on a CPU. Hardware considerations. Well, as we've just talked about, power is a major consideration. Neural networks processing is very computationally intense. This translates directly into thermal management. Most of our products are used in harsh environments, and environmental considerations are paramount. Many of our applications require fast frame rate or low latency, whether they are controlling a pan and tilt or we're looking at fast moving targets. Latency is a major consideration and a big performance parameter that our customers are focused on. Also, high accuracy is a demand. Low false alarms are important to our customer, particularly in our defense customers where they don't want to overburden operators with a constant barrage of false alarms. Cost, well, that's always a consideration. Development tools and employee skill sets. Talent management is a big challenge in AI. There are many costly type of skill sets that you must bring to bear to do a complete AI stack and integrate into an edge-based device. FLIR has made those investments, and we offer that to our customers. Technical support from the SoC and vision processor unit vendors. The reality is that purchasing power and scale are a reality, and that translates into the fact that certain customers or certain vendors have a certain threshold in terms of how much support you'll get from them. And so as you work to do deep integration of your technology into their chipsets, sometimes that's a difficult thing to gain access to. FLIR, with its scale, has direct and strategic relationships with the chip vendors, and we're able to bring tremendous value through the close technical support we receive from them. We have a series here of classes of hardware. We've got edge hardware here. We show this with like an Ambarella chipset for embedded, and then we could do a module around like something like an NVIDIA Xavier processor. And those tend to run in power levels between 1 and 30 watts. And then what we do on a server side, we'll use high power GPUs, and we use these machines for our network training. And then in the cloud, where we have basically unlimited compute power, this is where we do our machine annotation of our incoming raw data into our data lake, into our image cloud platform, so that we can do most of the work around annotation, doing machine learning, and it also allows us to do a search of vast amounts of data to build our data sets. Here is a table that gives some comparison about processor performance and processor capabilities. And what I've done here is I've baselined this on the CV22 from Ambarella. And if you look as you go up and down, as you go up into the NVIDIA platform, the Xavier is around 10 times the computational power of the CV22. But that comes at a very high cost. List price is around $900, and that does not include the carrier board that you would then mount the Xavier to, versus something like a CV22 or a CV2 or even the new CV5, where those price points are very low. The reality is that the NRE associated with building on a Xavier is much less than, let's say, on an Ambarella platform. So depending on the business case, you have to sort of select between low BOM and high NRE, or high BOM and low NRE. But again, our focus is on the latter, meaning we are focused on edge processing using the Ambarella chipsets. The next thing is we focus heavily on our data set development workflow. Well, we're focused on discussing hardware considerations in our product design. The ability to deploy camera systems with high quality analytics is totally dependent on the quality of the network training data. Here we illustrate our workflow and resources we use to create high-quality training data sets. Teledyne FLIR is in a bit of a unique place because image data for our applications and the wavelengths our cameras operate at is very limited. Many AI system developers can leverage open source data sets like ImageNet and MS COCO, which have millions of annotated images of dozens to hundreds of classes. To meet our needs, we've invested in data capture and annotation of images to create a data lake with millions of visible and thermal images of the targets our use cases dictate. To supplement field data, Teledyne FLIR has invested in synthetic data generation, which enables us to leverage computer image generation tools to create data sets where access, costs, and time severely limit our ability to create data sets using actual camera-generated imagery. Moving on, the next part of the process is the AI model development and workflow. And here, once we have a data set, we then go through the process of training the network, which is very computationally demanding, can take up to a week of server time to train a network across, let's say, 100,000 images. Once the network is trained, then we test it, we optimize it, and then we release it into our products. Because neural networks are so computationally demanding, we try to match the input resolution of a network to the specific use case. For Teledyne FLIR, most of our customers want the best detection at long range possible. To accomplish this, we deploy neural networks with large input resolutions of at least 512 by 512. This works well on thermal video, given commercially available infrared cameras have resolution of 640 by 480. However, most of our customers incorporate visible cameras in their systems and routinely integrate high megapixel cameras. Without additional techniques, images must be downsampled to match the network input resolution, resulting in a loss of pixels on target and range performance. To overcome this performance challenge, Teledyne FLIR has developed a software called NNTC, or Neural Network Target Classifier. NNTC uses proposal software routines to manage where the pixel input should be taken from an image. We use motion target indicators, a video tracker, and a number of other techniques to improve the system performance. Some of this is competitive sensitive, but I would be happy to discuss NNTC with you privately if anyone is interested. In conclusion, I'm very proud to represent Teledyne FLIR's deep learning team and present some of the innovations they've created. Please contact me if you would like to discuss our hardware, software licensing, or access to our data sets. Thank you very much.